Welcome to Bald Guy DIY. In this video, I'm going to tell you how transformers work, why we can't transform DC voltage, and how we get around that. Transformers are found all over the place in our modern society, from the transmission lines used by utilities to step down the voltage to our homes and businesses, to our electronics, or many other different applications in between. Now, whether they are huge or tiny, transformers all work on the same basic principles. In this video, I'm going to explain how transformers work, why they really only work with AC voltage, and how we can get around this or still use transformers in order to get a different DC voltage. The first thing that we need to understand is that anytime a current flows through a wire or conductor, it produces an electromagnetic field. Now, for electricians or anyone studying electricity, they use something called the right hand rule. You point your thumb in the direction of the current flow through the conductor, and then your fingers are supposed to curl, showing the direction of the magnetic field. Now, that might not seem very important, and I'm not going to get into much detail about it, but the important thing that you need to know for this video is that there is a magnetic field that's produced anytime that current flows through a conductor. Now, if your cable is shielded or it uses a metal jacket, it probably won't transmit that electromagnetic field anywhere. It'll kind of be broken up by the jacket. In the case of transformers, however, we're going to use the power of this magnetic field, and we're going to use it to transmit voltage from one coil to another coil and produce a different voltage on the other side. We also have transformers that keep the voltage the same, but for the sake of explaining this, I probably won't mention them in too much detail. So we have a magnetic field around our conductor, but when we shape our conductor into a coil with different turns, we also get a different phenomena that exists. Now, in answering the second question first, why we can't actually use DC voltage in a transformer, it's because the DC voltage is nice and constant. It's just continually the same value and also the same polarity or the same direction of current flow. Whenever you put a voltage into a coil, coils have an additional property beyond resistance, and that's called inductance. And inductance is something that opposes the flow of current. So as voltage is applied to a coil, you'll find that the current actually lags the voltage by a little bit. The reason for this is something called mutual induction, which means that as the magnetic field progresses through the different turns of the coil, the change in the magnetic flux opposes the flow of the current through the other turns of the coil. I don't want to make this too complicated. Simply know that the more inductance that a coil has, the more that it's going to oppose the current flow, the more interaction there's going to be in the magnetic fields of the different turns. Because of the way they're organized in the coil, they all interact with each other and create this phenomena. Now, when it comes to DC voltage, you're going to apply a constant voltage and a constant current that typically follows with it. Because of this, there's no change, and so the mutual induction that happens, it happens quickly one time, and then it remains nice and stable. While that's great in simple circuits because there isn't another variable, this inductance, that we have to keep in mind, as we do AC calculations, you'll find that inductance plays a huge role. But in terms of simple DC circuits, we mostly ignore it because of this instantaneous recovery from it and how it no longer affects the circuit. That also means that transformers, which use coils to transmit voltage over a magnetic field, don't work for DC voltages because there's no way to keep that magnetic field interacting in that mutual induction once the voltage stabilizes. AC voltage, or alternating current, is entirely different. Not only is the amplitude of the AC voltage changing constantly through the sine wave that you can see here, but also the current is doing the same thing. And not only is it going from 0 to a maximum value and down again, it's also changing polarity, which means that every time a full cycle of AC voltage is completed, you're going to see both a positive and negative, or a forward and back type action for the voltage and current. This might not seem like it matters a lot, but what that means is that 60 times a second, or 60 hertz, as we use in North America, that magnetic field is expanding and collapsing in two different directions. That means that it's always in a state of mutual induction, and there's always this extended magnetic field that's created by the mutual induction. That means that if you were to put two coils beside each other and only energize one of them, the second coil would have voltage induced into it through induction, and we would get a voltage output on the coil that's placed beside it. If all that sounds complicated, just think about this. In a transformer, or with this induced voltage, we're simply going to put one coil which is energized beside another coil which is not energized, and that de-energized or non-energized coil is going to have a voltage induced or transmitted to it from the first coil. That means that you're going to put voltage in on one side, and on the other side you're going to get a voltage out. Now, if we made those coils exactly the same size wire, the same number of turns, we would get the same voltage out that we put into it, minus a little bit of losses that occur because of the resistance of the wire and also some of the other factors in the environment or the other kinds of material that the magnetic field is traveling through. This type of setup with two identical coils is actually used in something called an isolation transformer, which separates two circuits so that they're not actually connected to each other physically, but it allows one circuit to produce the current and voltage in another circuit. But the most exciting thing about transformers is how you can start with one voltage at a certain value, and you can transform it or change it to another voltage entirely. We accomplish this by using two different types of coils, one with more turns than the other. So if we start with one coil that has 100 turns and the other coil that has 10 turns, the relationship between those two coils is 10 to 1, which means that if we put a voltage into the coil that has more turns, the voltage that we get out of the other coil will be 1/10 of the original voltage. That's because the turn ratio affects the amount of voltage. The current is also affected by that same 10 to 1 ratio. So whatever voltage we put in on the high side, or the one with more turns, on the other side we could get 10 times more current and have the same overall power on the input and the output. If you've ever taken a transformer apart, you'll likely see one side that has a lot more turns of a finer wire and the other side which has fewer turns of a much larger wire. That's because the finer wire, or the higher voltage, it doesn't need to have as large a conductor size because it's going to have a lot less current flowing through it than the low voltage side. On the low voltage side, there's going to be fewer turns, but it can handle a lot more current. And because current is what we use to size our conductors, the conductors themselves have to be larger. The net result is that the voltage times the current on the way in is going to be very similar, minus a few losses, to the voltage times the current on the way out. We can get almost unlimited possibilities from the same phenomena just by varying the number of turns in each coil. Of course, manufacturers have tested and tested different options, and so they know what works most efficiently with their design, but by changing these ratios between the low and high voltage sides of a transformer, you can create almost any combination. More advanced transformers also have many different taps or different options so that the same transformer could produce many different voltages or have many different voltages connected to it. The two major types of transformers that we think of as far as classification is a step-up transformer, which increases the voltage, and a step-down, which lowers it. On a step-up transformer, you're going to supply voltage to the side that has the fewer number of turns, and on the higher number of turns side, that's going to be your output. The exact opposite is going to work on a step-down transformer, where you're going to apply voltage to the side with more turns and receive voltage on the side with fewer turns. There's absolutely no difference to the function of these. It just depends what your starting point is and what you're going to get out of it. What you'll also find in almost any transformer that's available on the market, you'll find some kind of iron core that the coils are wrapped around. Now, depending on the design, they might be wrapped around separate iron cores, or they might both share the same iron core. But the reason the iron exists is because it's more efficient to pass a magnetic field through an iron core than it is through the air. When you use the air, it reduces the magnetic field quite substantially, but if you wrap coils around an iron core, you're going to have much fewer losses and a much stronger and more consistent magnetic field. I don't want to get too much deeper into the theory behind it because there's a lot of math involved, but the basic idea is that we can transform AC voltage because of its continually changing polarity and amplitude of voltage and current, and we can change them to a different voltage by varying the turn ratio between the high and low voltage sides. As I mentioned before, the reason we can't do this with DC is because the amplitude and polarity of the DC voltage are not changing, and so once that initial stabilization happens, there's no more inductance in the coil, and as a result, there's no way to transform it. So how do we change DC voltage from one value to another? Well, there are some electronic ways that we can do this using diode stacks and different things like that, but I'm going to leave the complexities of that for another video if people show some interest. The most common way that we use DC from the source is in the form of batteries, like our car battery or different 9-volt AA, AAA batteries that we'd use in our home. And in that case, you're going to size the batteries based upon the needs of the circuit that it's connected to. Everything is properly rated for the voltage that you're going to be supplying, and that's why it's important to use the battery that it says to use so that we don't overload our device with the wrong voltage. Also, underloading it could be a problem. But the way that we see transformers used when it comes to DC is that we usually start with an AC supply, which means that we're going to plug our device into the wall, and then some sort of process happens so that on the other end, DC voltage comes out at the right magnitude that we need it to be. One of the most common ways nowadays is that you're going to plug some kind of block into the outlet, and then on the other end you're going to have a USB connection or a lightning cord, something like that, that's going to plug into your phone or tablet or computer, all sorts of things like that. So how does it get from 120 volts AC, which is what we use most commonly in North America, down to only 5 volts for you to use and for it to be DC? Well, the first thing that we do is we transform the AC voltage. So we take that AC voltage that's very easy to transform, we run it through a transformer that brings it down to a working voltage that we need, and then we convert it to DC. A DC voltage can be obtained most commonly by using diodes, but again, that's a topic for another video. But all you need to know is that first we get the AC voltage down to where we need it to be, and then we rectify that voltage into DC so that it only travels in one direction. We can use things like filters in order to make that voltage more stable, and so that it doesn't follow that kind of sine wave path that we see of increasing and decreasing amplitude. And we can condition it so at the end you get a pretty nice clean DC supply that started with AC. That's how we get around it, and it exists in so many devices that you'll see all throughout your home, businesses, everywhere else. Anytime you have one of those cumbersome blocks to plug into the wall, it's not just there to annoy you and to make it difficult to fit other devices into the outlet, but it's actually a transformer that's going to take the AC voltage that's supplied and turn it down to the right voltage that'll work with your electronics. If you look at the transformer closely, you'll see the output voltage and current that it's rated for, and that's based on the transformer and the diodes that are used inside. I think that answers the basic question of how transformers work, why DC voltage can't be transformed directly, and also how we work around it. If you've got more interest in the subject, write me a comment below or send me an email. I'll do my best to explain it. There's also lots of online resources that explain it in greater detail. There are other ways to get different voltages and to convert things, but this one's the most commonly used because it's pretty efficient and it's pretty cost effective as well. If you enjoy these kind of videos, please let me know by giving the video a thumbs up, subscribe to the channel if you're not already a subscriber, and check back every week as I post a new video every weekend. My channel's grown a lot lately. I'm really excited about that. Looking forward to the future, creating content that hopefully my audience enjoys and will find useful. You can also email me, my information's in the description below, and I do my best to answer those as promptly as possible. Until next time, in all your quest for understanding, don't be afraid to be bolder.